For those of you that didn't attend last night, we covered quite a bit of territory, so we're kind of starting in a different place than we left here on Wednesday. Today I'd like to talk about the nonlinear characteristics or the linear characteristics of the bipolar differential pair. I'd like to talk a little about the common source amplifier, linearity characteristics, and then talk about offset voltages. We haven't spent much time talking about bipolar transistors in this course. But we looked at a lot of different op-amp architectures. In all those architectures, you can replace all N-channel transistors with NPN devices, all P-channel transistors with PNP devices. You'll have the corresponding counterpart or analogous bipolar op-amp. Compensation techniques apply in the same way as well, except you may have to, about the only exception is we don't have that nice triode region of operation for the compensation to move that right half plane zero back. Oftentimes we'll use a resistor for that in a bipolar process. Okay. So last time we looked at the linearity of the differential pair, the MOS device, and we saw that the signal swing was pretty much determined by V-excess bias. Everything, the linear characteristics were all proportional to V-excess bias. If you double V-excess bias, no matter what metric of linearity you get, you double that characteristic. We also calculated total harmonic distortion. And we observed that there was no even order distortion present in this differential amplifier. And that's due to the fact that we operate it differentially. And we found that the total harmonic distortion could also be expressed in terms of the excess bias voltage. And so we get analytical expressions for what the total harmonic distortion was. To make THD small, again, we want to make the excess bias voltage big. Now let's look at the bipolar differential pair. So kind of a refresher, in the forward active region, the collector current is governed by an exponential equation, and I've written expressions for the collector currents IC1 and IC2 in terms of the voltages V1 and V2 on that device. As for the MOS structure, we'll define the differential voltage to be the difference between V2 and V1. And then I can write, if I take the log of the first equation, I can write V1 is equal to VE plus VT natural log of IC1 over JSAE1. That's just the same equation written in a different form. And I can do the same thing for V2. And now I can take the difference of those two equations, and that gives me VD, and VD is now a function of IC1 and IC2. And the difference of the logs is the log of the ratios. So the JS cancels from those equations. And if we assume that the differential pair has matched devices Q1 and Q2, the emitter area of Q1 and the emitter area of Q2 cancels, and we have an expression that says the differential voltage is VT natural log of IC2 over IC1. Now, we know that IC1 plus IC2 is equal to I total, so I can then plug in place of either IC1 or IC2 an expression in terms of the other variable, and if I do that, I can get VD in terms of IC1 and VT in terms of IC2. But I don't really want the differential voltage, I want the currents, IC1 and IC2. So if I want to, I have the ability to solve this equation for IC1 and solve this equation for IC2. But for the purpose of determining linearity, we probably don't care whether we have an explicit expression for VD or an explicit expression for IC. Here's a plot of those exponential equations. And if you look at these characteristics, in contrast to the bipolar transistor, in contrast to the MOS transistors, excuse me, where we can steer all the current to the left or to the right, in this case, we can only asymptotically steer all the current to the left or the right. So the larger you make VD, the closer and closer IC1 gets to either zero or I tail, but it never gets completely to zero and it never gets completely to I tail. Okay. The other thing that's different is if you look at the slope here, the slope is typically much steeper than the slope for the MOS transistors. I wonder why that's the case. Difference between exponential law and square law. We had a square law relationship to determine that slope. In the MOS case, we have an exponential relationship that determines the slope in the bipolar case. So we'll do the same thing we did before. We'll put a straight line in and see where this line intercepts the VD axis, and that will give us some indication of the linear range of the device. It's pretty linear up to maybe half of that. So this intercept point here is at IT over 2, and I didn't write it on the slide here. Oh, I did too. The fit line that's the point slope form. I fit is equal to slope times VD plus H. That's the general equation of this line. So we see that H is equal to IT over 2. Now I need to get M, that coefficient of VD. How do I get M? Mr. Kimler.
How do I get M from the graph?
Or the analytical expressions. From the graph, first of all, what is M from the graph? It's the slope at the tangent line, right?
Yeah.
So I just need to find the tangent line at VD equals 0. So it's the partial of IC with respect to VD, evaluated at the Q point. Q point is where VD equals 0. So let's see. Well, I don't have the expression for IC here. Can we go back and get the expression for IC? So I don't have an explicit expression for IC, but I can take the partial of ID with respect to IC, the partial of VD with respect to IC1 here. Partial of VD with respect to IC1 is equal to VT times the reciprocal of this times the derivative of this with respect to IC1. Okay, so it's a calculus 1 calculation, and if I do that, I find that the derivative is minus VT IT over IC1 times IT minus IC1. Evaluate the Q point. The Q point is when IC1 is equal to I tail over 2 or VD equals 0. So the partial of VD with respect to IC1 is 4 VT over I tail. And hence M is the reciprocal of that. Someplace I should show that. So this is the fit line then. I take the reciprocal of that and put it in as for M. And now V intercept is H over M. Someplace that should appear here. So the intercept is at 2 VT. How big is VT typically? 25 millivolts. So the intercept's at 50 millivolts. Oh, man, I've got things going now. Is this a big swing? $50 millivolts. We can't even get 50 millivolts, and it becomes, we get about half of that. So we get about VT swing. In the Moss case, that intercept was what? What was it in the Moss case for the Moss differential pair?
I thought it was like 100 millivolts or 10, a factor of 10.
No, we had it in terms of the practical design parameters. Garrett, you remember what it was?
Was it root 2 VEB?
Root 2 VEB was this intercept. You're right. Root 2 VEB. So what can the designer do about that?
Control V.
Control VEB. Designers are control freaks, right? They want to control the characteristics. They can control it by changing VEB. In the bipolar case, what can the designer do about it?
Isolate the temperature.
Yeah,
That's it.
that's it. Or at a given temperature, can't do anything about it. Is that good or bad?
Pretty crazy.
It's bad if it's not acceptable. If this value is acceptable, it's good. In fact, it's real good because then you don't have to worry about process parameters or anything changing it. Only thing that changes is the temperature.
Doesn't that mean it's going to change itself though as we keep running? As we keep running our fabricated amplifier, it's going to,
With temperature.
yeah, it's going to cause.
Oh yeah, you take it outside in January in Iowa and it's going to go way down, and you take it outside in Dallas in the summer, it's going to go way up. As we did for the Moss device, we can look at the amount of differential input we can provide for X% deviation from linear. For 1% deviation is 0.56 VT. For 0.1% deviation is 0.27 VT. So 1% deviation is about 12 millivolts. 0.1% deviation, it's 0.2 times 25, about 5 millivolts or something. Not too big, is it? We can also look at measuring distortion in the spectral domain, like we did for the Moss device. I'm going to not go through all the details. It's posted in the slides. I put in VD equals Vm sine of omega t as we did for the Moss case. And then I solve for IC. And then I do a Taylor series expansion of that nonlinear function. And then I can plug in my differential input Vm sine of omega t, and I do a few calculations. Because these are the coefficients for the first and the second and the third term. Let's not worry about that. I recall a trig identity. Sine q of omega t is equal to 3/4 sine of omega t minus 1/4 sine of 3 omega t. So I get an expression for the collector current. And then I have this identity. I plug that back in. And I find that the collector current is equal to some constant, Q point, plus something times the sine of omega t, plus something times the sine of 3 omega t. So as for the Moss case, we observe the absence of what? What? What is oftentimes the dominant contributor to nonlinear distortion in an amplifier? Which harmonic? The second harmonic in a lot of circuits is the major contributor. A lot of times your magnitude of your harmonics fall fairly quickly as a function of the index. What do we see about the second harmonic? It's not there. Is that good or bad? That's good. Dominant form of distortion is oftentimes the second harmonic. There's no second harmonic distortion. In fact, this has no even order distortion. We could go ahead and look at more terms. It just has odd order distortion. THD we get by looking at the ratio of all of the harmonics past the first divided by the magnitude of the first. Is there anything that the designer can do to control the distortion? Well, you can control the tail current, but the tail current affects both the fundamental and the harmonics. And it affects both of them linearly. So the ratio, it cancels out. So the tail current won't affect linearity. In fact, if I look at the THD, I see it's only a function of Vm over Vt. So it's strictly a function of the magnitude of the input. Designer can't control it. For different magnitudes of input, for Vm over Vt of 2.5, THD is 13 minus 13 dB. For Vm over Vt of 0.1, minus 73 dBs. For Vm over Vt of 0.01, it's minus 113 dBs. Is this linear down here? If you have distortion, total harmonic distortion, minus 113 dBs down, is that a high level or low level distortion?
Low level.
Low level. A little low or really low? That's really low. It's a really low level of distortion. If you can tolerate Vm of 1% of Vt, oh man, Vt is only 25 millivolts. So 1% of 25 millivolts is 250 microvolts. So if you're willing to work with signals below 250 microvolts, there's not much distortion.
What if we conditioned the input before it got to our pair?
We can do that, but maybe there's something even better than this. Oh, here's a closed form expression for the THD. If we compare the THD, the MOS, and the bipolar structures, we see that both can be very linear, but the MOS structure strongly depends upon VEB. If you make VEB very large relative to VM, then the THD is not very good. So let's make a comment about using the MOS transistors to build a transconductance amplifier. Maybe the current mirror op-amp that we talked about, the one that's used often has open loop to build filters and voltage controlled amplifiers and so forth. The current dependence of GM of the differential pair is often used to program the transconductance of an OTA. So if you look at this OTA here, after it's fabricated, we see that for the MOS device, these will be now fixed after it's fabricated, and we see that the transconductance varies with the square root of the tail current, IABC. That's called the amplified bias current. That's usually the tail current of the device. And for the BJT, GM is equal to the bias current divided by 2 VT. So if we want to change the GM, it takes a 2-decade change in tail current to get a 1-decade change in GM. And if you look at the GM is proportional to V excess bias. So if you want to change the GM of a MOS device by changing the tail current, you're going to change the GM. And if you change the excess bias, you're going to change the signal swing. Signal swing was proportional to the excess bias for the MOS device. So 1 decade decrease in signal swing for every decade decrease in GM. If you decrease the excess bias a factor of 10 to change GM, I'm sorry, if you change GM a factor of 10, the only way to change it is to change the tail current, which correspondingly changes the excess bias. So if you have an input signal swing, you start it with a VXS bias of 1 volt, and you want a 1 decade change in GM, you're going to reduce excess bias to 100 millivolts. You reduce your signal swing by a factor of 10. If you want to get a 2 decade change in GM, you're going to have to decrease your excess bias by another factor of 10. So instead of being at 100 millivolts, you'll be down at 10 millivolts for VXS bias. If you want a 3 decade adjustment of GM, you've got to decrease the excess bias another factor of 10. You're down to 1 millivolt. When we talked about the OTAs earlier, we talked about how many decades of adjustment for those commercial parts of the GM.
Several orders.
Yeah, 5 or 6, right? We said for the bipolar structure, we could do 5 to 6 orders of magnitude adjustment of the GM. If we do a factor of 1,000 adjustment in the MOS case, our signal swing drops down to, our VX bias drops down to 1 millivolt, and our signal swing for reasonable distortion level might be 1% of that. So our maximum signal swing might be down to 10 microvolts to get reasonable linearity. Make sense? You might get decent linearity for large VXS biases for a MOS transconductor. But if you tune it very much, your signal swing is going to get really small. A bipolar device, there's the signal swing was only a function of VT. It was not a function of GM. So there's no change in signal swing when GM is changed. So the bipolar device might start out with a lower signal swing. The signal swing is comparable to VT, 25 millivolts. But after you do a little over a decade adjustment with the MOS device, your signal swing in that MOS device is already going to be less than the bipolar device. And if you go down smaller GMs with the MOS device by adjusting the tail current, the MOS device comes grossly less linear than the bipolar device. Is that clear? So large GM adjustment range is possible with a bipolar differential pair, several decades of adjustment, because the signal swing is not dependent upon the GM, but you have very limited adjustment capability on the MOS structure because the GM changes as you change the signal swing changes as you change GM. Now, we looked at that bipolar amplifier, And we saw that if we wanted at most 1% deviation from linear, if I recall, our signal swing was restricted to about 250 microvolts, right? Started out at 25 millivolts, and we said if we want about a 1% deviation from linear, we're stuck at about 250 microvolts. And if we have a little bit smaller signal swing, we had 113 dB THD for that structure. Let's go back and see that. So if VM over VT is equal to 0.01, we have 113 dB of linearity. So now let's look at a bipolar amplifier, a bipolar operational amplifier, and get some idea about how linear it is. So if the gain of that two-stage op amp built with a bipolar differential stage is 100,000, and the output voltage swing is 10 volts, the input voltage swing that appears at the differential pair will be 10 volts divided by 100,000, will be 100 microvolts. So if we ask the question, is this bipolar amplifier linear when used in an op amp? What's the answer? Yes, it's very linear. If you look at the total harmonic distortion that you have, because of the nonlinearities in those bipolar stages, it's going to be quite a bit better than 113 dBs. Make sense? So if you use the bipolar input stage, which looked highly nonlinear, as the first stage of a high gain amplifier, the amplifier is very linear because your signals are so small. It might get worse when we get to higher frequencies because the gain rolls off, so we don't keep that gain of 100,000 at higher frequencies. Let's look at the linearity of the common source amplifier. So I'm going to put a signal into this gate of this common source amplifier. And as the gate to source voltage changes, I'm going to correspondingly have different currents flowing. So I've got three different curves here, VGS1, VGS2, and VGS3. I'm going to assume the quiescent value is 1 volt, and I can go down to 0.99 volts or up to 1.01 volts. So this would be a 10 millivolt change in the input voltage. And this is the constant base current line. I'm not biasing with a constant current source. So then I can project down and see what the corresponding VDS values are, which determines the output voltage. And at least from this plot here, it looks like that it's pretty linear. As the input voltage changes by plus or minus 10 millivolts, it looks like it goes up and down about the same amount on the output. But we can be analytic with that. So if I equate the drain current to the bias current IB, I get this equation here. And from this equation, I can solve for the small signal output, the out small signal, and it's equal to the VSS minus V out Q, and then minus this term here that's a function of Vn, and as a function of small signal input. Well, it looks like it's nonlinear because the small signal input appears in this squared expression. However, VM small signal is probably going to be small compared to V excess bias. And consequently, we can do a truncation of the squared term after first order terms. And we can do a Taylor series expansion to put it in the numerator. And if we do that, we finally get this expression that the small signal output looks about like this. And we see a quiescent term. We see a linear term dependent on Vn, which is what we want. And then we see a term that's dependent on Vn squared, which is what we don't want. It's an amplifier, so we don't want that squared term. Now, you can show that a squared term in the polynomial expression corresponds to a second order term in the spectral characterization. Vm sine of omega t squared is equal to what, 1 plus cosine of 2 omega t over 2. So this is going to give rise to the second harmonic. So we didn't see that second harmonic in the differential stage, but we see that harmonic in the single-ended stage. And usually that second harmonic that we get in the single-ended stage will be bigger than that third harmonic we get in the differential stage. So I've simplified that expression. Again, I won't go through the details. They're in the posted slides. And we can see that we can express the small signal output in terms of the practical design parameters, in this case just the excess bias on that device. And now we see the magnitude of the second order term relative to the magnitude of the first order term. And what can we do to control the distortion here? So here's the small signal output. Now in terms of these practical parameters really look nice, don't they? Because we had these ugly expressions in terms of the natural parameters. We get back these practical parameters, and we have a pretty simple expression. Ms. Poon, what can we do to improve the distortion? What does the designer have control of? The excess bias. So if you want to get low distortion, you want to make the excess bias what? What? Usually we want low distortion for building amplifier. So as a designer, what do you have to do to get low distortion? Make V excess bias high. If you make V excess bias high, you make this coefficient small relative to this one. But it's at an expense. The gain is this term right here. So if you want low distortion, you're going to have to live with what?
Low gain.
Low gain. Is that clear? So when you get this form, it's pretty easy to see what the designer controls. It gives you some idea about the relationship between the gain and the distortion. But if you looked at the previous form on top, man, what a mess to figure out what's going on. Well, it's pretty clear that this is a nonlinear relationship that we have here. But we can control it with the excess bias. So here's a plot of the output characteristics of the common source amplifier. We see that as the input voltage changes, the output voltage varies non-linearly. Here's a fit line. So if you want to keep things in saturation, the minimum value of V in small signal is V excess bias. And if you put in a value of V in small signal V excess bias, you'll find you have 50% distortion. So the signal that you want to put in needs to be a lot less than V excess bias. You'll still be in saturation for certainly smaller values of the input than V excess bias. But if you get anywhere near V excess bias, your distortion gets really large. However, if you look at the structure, it's a reasonably high gain amplifier. So if it's a high gain amplifier and you put in if the gain of the amplifier was 100 and you put in a signal of V excess bias of say 1 volt, you'd have 100 volts at the output. So we don't really have to worry about putting in big signals in this amplifier because we'd saturate the output anyway. So we can ask the question, over what output voltage range are we really interested in? And we see that if you have a fairly high gain on the amplifier, you're really only interested in the input that's equal to the output swing you want divided by the gain of the amplifier. So we may only be interested in small signal inputs that are in the few millivolt range. So if your inputs are in the few millivolt range, we see that this amplifier is really quite linear. Okay. So the practical input range for this structure is much less than V excess bias. V excess bias is the maximum input, but you have to divide that range by the gain of your amplifier to see what your input range of interest is. So here we're putting a small signal input of plus or minus 20 millivolts. We've designed it with an excess bias of 1. And we really don't even see the nonlinearity in this plot here. So here's one of the simplest integrators that we can build. We can take a transconductance amplifier and drive a capacitor, and we saw earlier that that would form an integrator. And we can put integrators together to form arbitrary filter structures. And the MOS transistor itself, or the bipolar transistor, makes a reasonably good transconductance amplifier. So could we just use the circuit on the upper right as an integrator? The nice thing about that circuit is it will operate up into the several hundred megahertz range or higher in probably a 0.18 micron process. And if you get down to 60 nanometer process or lower, it might even operate in the gigahertz range. I did the same thing for the bipolar structure. So we can ask the question whether this is linear or not, and it's reasonably linear if we use it in high gain applications. But if you use it in low gain applications where the gain is the order of magnitude of 1, where the signal at the output is comparable to the signal at the input, then it's highly nonlinear. Well, let me leave it. Let me leave it at that. So we've got at least analytical expressions for looking at the linearity of both the bipolar and the MOS common source amplifiers. Let's talk a little bit about offset voltage. There are two types of offset voltage: systematic offset voltage and random offset voltage. And by definition, the offset voltage is the difference between the desired output and the actual output when V and D equals 0. And V in common is at the quiescent common mode input. So if I connect the inputs together, put the input at the common mode input, then the output offset is the difference between what I want and what I get. A lot of people define it to be the difference between V out and 0, but I define it to be the difference between V out and what you want it to be. And we typically refer the output offset back to the input by dividing by the gain of the amplifier. So the input offset is equal to the output offset divided by the gain of the amplifier. After fabrication, when you go in the laboratory, if there's offset, you can't tell the difference whether that offset came from systematic offset or random offset. At the design stage, you can tell the difference. But once you're in the laboratory, you can't tell the difference. Measurements of the offset voltage for a large number of devices will provide a mechanism for identifying the systematic offset and the random offset. So you take one device and measure in a laboratory, it has an offset voltage. Take another device and measure it as an offset voltage. If you don't sort your population, the random offset will be Gaussian zero mean. So then you can average the offset voltage of a bunch of devices in your population, and that average value of the offsets will be the systematic offset. And then any deviation from that for individual devices will be the random offset. So for a single device, you can't tell the difference between the random offset and systematic offset. But if you have 1,000 devices and average the offset voltage for all of those devices and subtract that from what you measure for an individual device, that will be the random offset of that individual device. I want to make a couple more comments about random offset, but we're way past time up. So we'll touch on this on Monday. That's all for today. Thanks.
Could we aggregate across different